Yes, I'm trying to go live on YouTube streaming. So start recording on this computer. Okay, so just to give you an idea of where we are. Yeah, today Diganta won't be able to join as he has some other commitment, and therefore we are juggling a little bit. So, well, we lost one day for the holiday. So what, okay, like one, yes, the reason, okay, we are kind of here. So if you had last Wednesday's, this Wednesday's class, what we wanted was to have Diganta discuss this big ACAS, which is one of the larger benchmarks on which these techniques have been used. ACAS example, that's DNN, that's been built and trained. It's a flight collision avoidance system. And we are planning to have you work on different parts of that network. That's a fairly big neural network for your project. And therefore, we wanted to discuss that even before we get more into the SMT algorithm details and some of the other tools. But unfortunately, Diganta could not be here. And we are also, I had not covered the modeling of neural networks. So part of, August 26th, that neural network modeling example we had deferred. And that I will cover today. And I'll also cover what is kind of not this one, concepts of over and under approximation. Using programs as example. Okay, some of that, if time permitting, I'll also cover that. And the ACAS example will be discussed next Wednesday. Okay, if not sooner. I mean, as we have been, I'm falling behind by 1 or 2 lectures. We may want to make up for one class. For the to make up for the holiday, but we'll decide that, and maybe we'll use one of the tutorial on Thursday. So this lecture schedule is fairly accurate up to the midterm exam week. Okay, we want the reason we want to cover the ACAS example is because so you will be studying that, reviewing the example and experimenting with it on your own while we define, and the project itself most likely we want to define by the midterm week, so that you will start at least thinking and about it, and probably working on some exercises that we'll be giving to help you warm up towards that before the exam week. And I also plan to give one more assignment. By the way, your assignment on TensorFlow is due. I think most of you have submitted it. If you have not submitted it, please do. So we will grade it and give it to you. And I plan to have one assignment. I don't think that assignment has gone on Z3. Okay, so that assignment will go out sometime this week. So you could be working on that while you will study the ACAS example. I will try to, I will, certainly update the schedule, completely, and then upload it onto Moodle by next week. Okay. So as I said, today's topic is illustrating through an example how you would model neural network logic and the property. Yes, is there a question?
Yeah, can you hear me, sir?
Yes, I can hear you.
Yeah, so you were talking about the assignment. So we have submitted the first half of the assignment, like the first 2 questions, as Diganta had said the deadline for that was 19th August. But I think you haven't changed the deadline or anything for the complete assignment. So that's why I think most of us have not uploaded the complete assignment.
Okay, so why don't you, is it fair for me, by Monday, can you submit?
Yeah, yes, sir.
Yeah. So let's have that. I will make an announcement this week, because I'm going to put out an assignment for you on using Z3, some Z3 problems. Yeah.
Right. Yeah. So Diganta was telling us that this week will be the deadline someday in this week. So Monday works. That's not an issue.
Yeah. Okay. So the topic of today's paper, networks and over and under approximation. I'll introduce that not in a very formal logical way, but through examples. So they are topics of this chapter. So this is a very easy to read book. Chapter 2 and 3. Okay, what I'll be covering today, and some aspect through examples of what is discussed in a very formal way of chapter 8. Okay, there's lots of details in chapter 8, but I'll be discussing some of those concepts, like over and under approximation. Over approximation is certainly discussed here using certain what are called abstract domains. But the theory, there's a little bit more theory in chapter 8. We may cover it later in the thing, but it's important that you understand what abstraction and over approximation means. So that's the reference book if you want to consult it. Okay. Oh shoot. Oh, whenever I lose this. Yeah, that's okay. So, yeah, I want to briefly get back to this example that you've already seen. So this kind of shows how, the behavior of a program, in this case, a sequence of simple assignment statements followed by a return statement, can be modeled by using logical variables. I call them timestamp logical variables with one timestamp variables to denote the value after execution of every statement in the program. Okay, so now sometimes this is also presented in the here. Okay, is there any question about about the way it is presented here, about any questions about why you're not sure that this formula actually models the return value. Okay, I hope you understand that. No question, no doubt there. So if there is none, then sometimes you also, you could track these values in a slightly different way by not using timestamp variables like it is done here, to denote the value after every statement, but only the a logical variable corresponding to each program variable, then you can define a predicate. I'm showing you this as an example, okay, because I'll be using this later on when I discuss over and under approximation. Each of these is a formula which is defining, you can say, a predicate which characterizes the values that the program variables may take. Okay, this predicate, it denotes the set of values that the program variable can take at that location. Okay, for example, upon entry to the function, there are some initial values. So this formula, it says x is equal to some value x naught, y naught, and z is equal to z naught, where x naught, y naught, and z naught can be some arbitrary value. Now, after the first assignment, z is equal to y, that is what I consider as location 1. This predicate here captures the the set of values that you can that the variables can take after the first assignment. Okay, so anything that makes this formula true is a possible value that the program variables can have after the execution of the first assignment. Okay, for example, because y is assigned to z, so after that assignment, z will be equal to y, both of which will be equal to y naught, the initial value, and x is unchanged, so it is x is equal to x naught. So each of these is called the it's a predicate. Okay, a formula defines a predicate. I mean, I keep calling them as a predicate because after all, this formula defines that predicate, and is usually this one is this way of characterizing what the set of possible values of each assignment is something that you can say the strongest and the most accurate thing that you can actually say about the possible values that the program variables can take at that location. Similarly, if you do the second assignment, which assigns x to y, what will happen? The value of y changes. Okay, so y becomes equal to x, and which whose value is x naught. And z, the value z remains the same as before because that's unchanged, and so on. Okay, so each of these is a statement in terms of a predicate which captures the set of values. It's precisely the set of values that those program variables can take. So at the exit point after the return statement, R1, the return value, which is the logical variable that holds, is y naught equals y naught. Okay, this is another way of capturing that behavior. After that, then the property that you want to verify is given x naught, y naught, z naught, and R1, R2, that you want to show R1 is equal to R2. So this is just to illustrate two different ways. Now, the one that I've shown on the right side, I've given you very informal. There is a very well-established theory called a specialized logic called Hoare logic, which define how to derive these predicates given any predicate that captures the initial value at the entry point, arbitrary predicate expressed as a formula. Hoare logic, which I will not cover, okay, in detail, it gives you rules to derive these predicates after each statement in a programming language, okay? And that logic is due to one famous computer scientist named Hoare, and he has developed that logic. And that can be automated. It's a specialized logic built on top of first order predicate logic like SMT logic. And that gives you the rules that will tell you how to precisely get these predicates. Once you get those predicates, then any property of this kind can be shipped off to an SMT solver to check, just like you did it here on the left side. So there was it's a different way of capturing that in terms of timestamp variables. You see the number of variables here is that the formula that you will eventually be shipping to SMT formula has more number of variables, and it's a more complex than this way of doing it, where you do this through what is called predicate propagation by deriving a predicate that captures the reachable values after the set of values that the program variables can take, just contrasting it. Okay, so any question you have about this? Is it I mean, conceptually clear as to what these predicates mean? Any questions? Okay, so let me move on. So now let me take the example, I mean, how we could do, take an example of a neural network. Let me minimize this. Okay. So here is a neural net, synthetic neural network, not derived. The weights are not derived by any kind of training and so on. What this is, it is supposed to given, it has an input layer with two nodes. Okay, so two input values, x0, 0, and x01. And it has two layers and an output layer. Okay, so I have split, as you know, that the neural network at each of the hidden layers has okay, some question here. Enlarge the PDF. Okay, sure, I will do. This is not good, isn't it? Maybe I'll do it this way. Is it better? Is it better, Jyoti? Dhruva Jyoti. Okay, thank you. Good. Okay, so I've just shown here in this diagram the linear transform that is applied, and after which the activation function, which in this case is the ReLU function, are shown as two separate nodes. I've split that by using one set of node for that takes the value after the linear transform, and similarly after that the ReLU outputs will be fed as the input to layer 1. So this is layer 0 and this is layer 1, and then you have another activation function, application of activation function to produce the output layer. Okay. So this one, 500, and so on. So they are just, for a particular value, it shows what the value would be for the case where G is equal to 1000. But basically, the idea of this is supposed to calculate the maximum of the two inputs. Okay, like any DNN, this does it in a approximate way, as I'll explain it in a moment. But basically, if x00 is greater than x01, then it is supposed to put out a value of 1 for x20, and a value of 0 for x21. and vice versa, okay? If it is, if x00 is less than or equal to x01. Intuitively, so what it does is it captures, so G is kind of the, weight, here it is kind of, I've shown it as parameterized, okay? And let's first, for the moment, assume G is equal to just 1, okay? And so the way it does this, once again, it's not in an artificial way. So it computes, the first two nodes compute x00 minus x01. And the inverse of it, x and y01 is takes the computes x01 minus x00. The other two nodes, y02 and y03, they do the same, except that they are there is a bias of -1, so they're shifted by -1 by using a bias of -1. Okay. After that, so and that's what that's what it does. Therefore, that ReLU is applied. And then you take, yes, okay, the difference of the outputs of those things as the linear transform applied to produce y10 and y11. So, so the reason that it works, at least in most cases, is that so in general, it works. Okay, is that clear? What the thing does? Okay, structurally, what it does. Okay, so the reason it works in most cases is because if x0 and x01, the difference between x0 and x1 is significantly larger. Okay. It's significantly larger than 1. Both the, if x0 is greater than x01, then what happens is significantly larger, because then both these values, y00 and y01, will be positive. Okay, if x00 is much significantly larger than x01, more than by 1. Okay, because the bias is -1. Then both of them will be positive. And they will, yes, both of them will be, positive. Then those get, they get passed through the ReLU, and y10 will then be just the this one, okay, because it takes the weighted difference between these things, x0 minus x1 and x0 minus -1. So that because it just takes the difference between those two values, and that will be that will be 1. Whereas on the other hand, if x0 is smaller than that, then both will be negative, and the ReLU output becomes 0, and therefore x21 will be 0. Okay, so this works as long as the difference between the two is greater than 1, larger than 1. Okay. The reason it doesn't work in all cases is because if the differences between the x0 and x01 is smaller than 1, then this x00 minus x01 will still be positive here, and therefore that will be passed through the ReLU as is. But this one, x01 minus x00, will be negative, because if the difference is less than 1, the second output, y01, will be negative. And if the input to a ReLU is negative, this becomes, 0, okay? Yeah, and since this difference is less than 1, that gets passed through, okay? And y10 will not be 1 exactly, but it will be something less than 1, positive, but that gets passed on to the thing. So if the difference between the inputs is less than 1, then the intended behavior, which expected behavior, is we wanted the output to be 1 when output to be 1 whenever x0 is greater than x01 will not hold true. Okay, and it's the same case for the other case when the difference is when x00 is less than or equal to x01, but the difference is less than 1. So you will see that in that case also the output will not exactly be 1. So that's why I said that in this kind of approximates, this neural network approximates the computation of the task of computing max. Okay. Of course, the reason that I've left G parameterized here is because to exactly address that concern. Now, if I choose G to be arbitrarily large, then the cases for which this network does not produce a 1 whenever x0 is greater than x1 can be made as small as possible, and that's because you see, because that gets what you get is G times, if you have a G, then it'll be G times x0 minus x01. Therefore, then the tolerance on the difference for which it does not behave will be much smaller. It will be actually 1 over 1 over G. Okay, so and then by making G as large as possible, you can reduce the range for which this does not produce accurately 1, 0. That is the idea of keeping G as a parameter. Okay, so is that clear as to why, how, in what sense it approximates the max function, and the fact that G can be by choosing large enough G, you can make the the tolerance for this deviating from the design specification as small as possible. Okay. So given this, for example, we said that there are various different categories of properties that you want to verify. One is one class of properties called a safety property. This is an example. This is a property belonging to this category captures whether the behavior, the network, behaves for all inputs, meets the intended specification. Okay, which in this case is that it should produce 1 whenever when x00 is greater than x01 and 0 otherwise. Okay. Now, obviously, this can only, since it implements that, you can still prove as long as the difference between the thing is x0 minus x01 is, I'm sorry, x01 minus x0 is 0 is, x0 is less than this tolerance, 1 over G, then x20 will be 1 and x21 will be 0. Okay, that is, the difference should be greater than that the tolerance of error that it is permitted. So as long as that precondition is met, then the output, so here I've denoted by n, the script n, the overall functionality of the function implemented by this neural network shown above, so that if that applied to its input produces the output x20 and x21, and if the difference between the two is greater than 1 over g, which is the tolerance of error that is permissible, then x20 will be 1. So these kinds of properties that capture whether based on certain input constraints, as long as your input satisfies certain tolerance constraints, if the network behaves as it is intended to, that such properties are called safety properties. Okay, I'll get to showing how the network itself can be modeled as a formula. Okay, how the script n can be modeled by in a modeling of the network, just like we modeled the program in two different ways. So if n, this part here, n, models the functionally the behavior of the neural network, and the precondition on the inputs are satisfied, then the output it takes the value as expected. Okay. Yeah. Similarly, when it is the other one, so when it is x00 sufficiently smaller than x01, then for the other case where when x01 is greater than x00, x20 will be 0 and 1. So these two formulas then capture the expected behavior as long as your input satisfies the tolerance constraint. Okay. So is that clear? Any questions here? Okay. In a moment, I'll show you how this n can be modeled also within the logic that we have presented. So, but given that, I hope you understand how this particular safety property that I just now stated is modeled by this SNT formula. Similarly, a robustness property, an instance of a robustness property, is something where, which says how well this, how it departs, how well if the inputs are perturbed by a certain amount, if it's still and and the inputs satisfy the input tolerance level, if it continues to implement the max function as intended, okay, with x20 returning 1 and x21. So here the perturbation is defined by introducing two new variables, x00, x01. They denote the normal variable, and x00 prime and x01 prime, they denote the primed variable denote the perturbed, the variables that are you get if you perturbed it in a certain way. So here, so that, and if on the perturbed variable, the output produced is corresponding prime variables, which is defined by n, and as see this part here specifies what the tolerance on the perturbation is, as long as the values are perturbed within a certain tolerance level, which in this case turns out to be as long as it's less than 1/2g, okay? And your, your input still satisfies this accuracy constraint that your, that the difference between the inputs should still be bounded by 1/g. Then, as long as the perturbations are within this tolerance as described, the output will be equivalent. Okay, the two output, the original output, and the output produced for the value that is the perturbed value. Okay, as you can see, these statements are very general statements. Okay, because we have used logical variables for inputs and the perturbed variables. So this captures, in some sense, the property, the robustness property for all possible perturbations that satisfy these tolerance constraints. Okay, so, and you can also see that while we had to use only a safety property in order to model a safety property, you needed to invoke the network only once logically, and whereas here you will have to, the formula has to have two copies of that function. One that produces the output values, the original input, and the other one on the perturbed, tweaked, the perturbed input values. Okay, so this is how you specify, once you model the network itself in terms of in this case define it as a function, and you will see how we can model it as a set of formulas. So given that the outputs are as specified by the model of the DNN, and all the inputs, a certain tolerance constraints are satisfied, then your two outputs, the original and the output on the perturbed input, they'll have to be the same. Okay, so this is how you typically specify the properties. Of course, these specific safety property can, it's very domain specific. The kind of property that you want to, it of course depends on your expected, what your expected behavior is. And so it may change, but I hope you got the basic idea of how you could specify, given that the DNN is modeled, okay, separately. So any questions here? Okay, so now let me get to what means to model, how you could model. See, one way to model this network is to treat it like a program. Okay, after all, each layer has its own variables here. Okay, much like you did in this case. So you could treat them as a sequence of assignments where your y00, or I'm sorry, this should be x. Yeah, layer 0, the x10 could be defined in this way. Okay, this should be x10, sorry. For example, x10 is the result of applying this linear transformation denoted by corresponding to the linear transformation applied to produce y00, and that is captured, say, by this function, okay? And then your ReLU is just like an if-then-else statement. You could capture that as an if-then-else statement. And you can have, you can represent this as a sequence of assignments, which gives the, for each nodes in each layer. And then you can use the kind of transformation that we did for as illustrated for the program, okay, that I showed you. Of course, I didn't show you, I showed only how you could model by using timestamp variables for simple assignment statements, whereas here in this case, a ReLU function will denote an if-then-else statement. So I didn't tell you how exactly you could capture a ReLU function, the if-then-else conditional statement in a program. And that's why I'm showing you here how you could directly do that, okay? For example, ReLU. So the ReLU itself, this one here, this arrow here, which relates the input of the ReLU to the output, okay? So given the input to a ReLU function, in, some signal in, and out, so it exactly says what, how it constrains the output in terms of the input, okay? So this formula on the right side, okay, which defines the ReLU formula, just says that if in is less than or equal to 0, then out is equal to 0. And, okay, so the output the output of a ReLU has to satisfy both these constraints. One constraint for the case where in is less than or equal to 0, then out must be equal to 0. If in is greater than 0, then out will be, it has to pass the input unchanged. So out will be equal to n. So this is a generic way, this formula is a generic way of capturing the constraint imposed by the ReLU function. Okay, so that's how a conditional statement, an assignment statement, would be modeled as a formula. Any questions here? Do you have any doubt as to how this formula here captures the constraint imposed by the ReLU on its output? Clear?
Yes.
Yeah, there's some question here. Oh, Sudakshina. Okay, Sudakshina, that is an unpublished book, okay? It is not published yet. I don't think it has been formally published yet. I'm not sure. The last time I checked, it was not published. It is, the author is one House. His last name is a little bit hard to pronounce. But I've stated there. But I have uploaded a copy of it on Moodle with his permission, okay? With the understanding that you will not circulate it, okay? Okay, sure. Yeah, so given that, then here is the, the entire formula that models the behavior. By the behavior, I mean it captures exactly the constraint that x2 0 and x2 1, which is the output nodes, the value of the output nodes, ought to satisfy in terms of the input variables x0, 0, and x0, 1. So it is structured as per the thing. So pretty much, for example, y0, 1, y0, 0, this one defines the value produced at that node y0, 0, which is simply g times x0, 0 minus x0, 1. That's what is captured by the f01 function, which I've denoted on the right-hand side here in this assignment statement. Similarly, y01 is defined by this expression, and so on. y02 and y03, they are two shifted by 1. And then you have several instantiation of the ReLU constraint on the respective inputs and outputs, because there's one ReLU constraint for each ReLU instance of the ReLU activation function used here. 4 in this layer and 2 in the second layer, in layer 1, and 4 in layer 0. So so this is a big conjunction of these formulas, where the ReLU constraints themselves have 2 constraints, each of which is an implication. As you can see, by what theory is this formula? What theory is this formula under? It's an SMT formula, and since we allow so the domain over which these variable range to be real. I mean, presumably it's over the real number. So this is a formula, an SMT formula in the theory of linear. Okay, assuming G, well, I've shown it as a parameter G for any particular constant. Instantiation of G by a constant, this entire formula will be an SMT formula in the theory of linear real arithmetic. Is that clear? If you leave G also as parameter, then it is no longer in the linear real arithmetic. Notice that this is not a formula that you can ship off, ship it to an LP solver, okay, and expect it to solve this property. Okay, this is what I've shown here is what will replace as in place of n here, okay? So nx00, this equality that I've shown here, from here to here, you need to replace it with this big formula, okay? And that formula is what you would then ship it to an SMT solver to check that this formula is true, is valid, in the sense it is valid for all possible inputs. Now, where you check validity, you take the negation of this formula and then ship it to an SMT solver and see if it is unsatisfiable. Okay, that's what that's what you do. Now, my question is, this formula cannot be sent to an LP solver. Why? Can someone answer? Anyone? What does an LP solver solve? Okay, it solves only a conjunction of linear inequalities, correct? How is this different, this formula? Anyone? Is it simple conjunction of linear constraints, linear inequalities? Why? I say no. Why is it not strictly linear constraints? Each of this is an equality. So up to here, it is linear. So from here to here. Now, where it departs from linearity is because of the ReLU function. Remember that the ReLU is a conjunction of 2 implications, and an implication is not a conjunction. Okay, if you convert Messier formula, it has a disjunction. Is that clear? You have to say yes or no. Okay, I mean, it'll help me to say if you're yes. I mean, otherwise, what am I to assume? So, can someone say yes? And if it is not clear, please.
Yes, sir. We are we are doing it on the chat.
What?
Can you check the chat?
Yeah, ReLU is non-linear. ReLU is non-linear. See, there are two things, okay? ReLU is non-linear yes, it is non-linear. It's not strictly linear, but you will see that there also, yeah, and the linearity here is because of this. It's also this Boolean combination. The Boolean combination is an arbitrary Boolean combination, okay? So ReLU is non-linear. That is one way to put it. And ReLU has two conditions, yes, okay? Yeah, when you want to answer, please unmute and then answer so that I don't need to go and then look at chat. Yeah, that's the correct answer, and that's why you need an SMT solver to be able to solve it. Okay. Now there are, you see, I mean, the reason is, so there are other activation functions like sigmoid, sigmoid, which are non-linear. Okay, but they don't have a logical structure which take it outside a conjunction of linear inequalities. So there are two sources of issues as to why an LP solver will not be able to solve it. One is that the kind of non-linearity you get due to multiplication and so on. The other kind is the logical structure, okay? That is also, in a way, when you view it in terms of linear theory, it is non-linear, okay? But that logical structure complicates the thing, okay? In the case of, comes in the way of using LP solver. And that's why if you, SMT solvers, they do support non-linear real arithmetic. Okay, although it is non-linear arithmetic. In that sense, you can you'll be able to handle both the logical structure which goes beyond just solving a conjunction of linear inequalities, but rather any Boolean combinations, and it can also solve non-linearity in the sense of having x times y kind of arithmetic expressions. Both are the bottleneck for LP solver, which use of SMT solver allows you to do. Okay. Yeah, that's those are the points that I wanted to make. Any questions here? Okay, this is how you will be doing. Of course, you could, for example, sigmoid. You need to have. You can either, sometimes sigmoid and those kinds of function. If you want to precisely capture, you need non-linear real arithmetic. But there are linear approximations that you can actually use and stay within the conjunctive fragment of linear inequalities. But in some cases, like ReLU, you will end up going outside of the usual conjunction of linear inequalities, which LP solvers are restricted to. Okay, so that's why using SMT solvers you can do that, and we will see how certain specialized decision procedures have been developed in order to address these kinds of constraints that ReLU activation functions produce. Okay, so that finishes the first part of the things. In the remaining 15 minutes, I want to spend it on illustrating what it means to use. In this case, the property, by the way, is it clear as to why you need two copies? As you can see, the proving robustness property, I mean, the size of the formula is what? The work that an SMT solver has to do in order to check satisfiability of these kinds of formulas is a function of the size of the formula, where the size of the formula is the number of variables that appears in it and the number of clauses that make up the CNF representation of this formula. When you reduce this into CNF, the number of clauses that you size parameter in typical realistic networks, even though the number of layers might be only a few, but the number of nodes in each of those layers will be, quite a few running into, hundreds of thousands of nodes. And you can see that since you need to have one kind of, one equation to capture for every node, and ReLU will introduce these kinds of implications. So the number of clauses will grow very rapidly. Now, for robustness property, you do need to make two copies of these constraints, one for expressing the constraint on the original inputs, and another for expressing the constraint, the outputs on the perturbed input. And therefore, you see, this is strictly harder thing to solve in an SMT solver when compared to a safety property, which requires only one copy of the network. Okay, so sometimes if you capture it, the behavior in a precise. This is true of program verification as well. Okay, and in some sense, neural networks are simpler than a general arbitrary program, because the control structure is fairly simple. I mean, because the neural network really is a sequence of assignment statements of this kind. Okay, whereas programs have if then else and loops and jumps and so on. So they introduce their own complexity. In that sense, the DNN is easy to solve, but the size of the DNN and in some cases, I mean, the nonlinearity it introduces, they add complexity. And of course, there are variants of neural networks like recurrent neural networks, which also have loops, okay? And then your complexity will be close to any program, okay? But sometimes you can exploit the fact, if they're ordinary DNN, you can exploit the fact that it does not have loops in order to simplify at least the formula that models it, okay? So in general, this doing it this way, directly modeling it precisely, the output, the constraints, imposed by the network precisely, will not scale in practice, and therefore we use this concept of over approximation, and that's what I want to introduce, illustrate right now what it means. And in your project, you will be using, because what you will be checking is certain property huge
Sir, could you check the chat, please?
Is it better now? If I'll make sure that I'm close to the thing. Is it better now? Say yes.
Yes.
Oh, for the last 3 minutes. Yeah. No. Yeah, I will do that. Yeah. Yeah, I did. It worked in a precise fashion, like I've shown here. The n part here. Sometimes the formula becomes too big, or the size of the complexity of the problem is too big, and therefore sometimes you will have to introduce what is called, we deliberately introduce imprecision in a sound way, and that's what is called abstraction. So that sometimes simplifies the complexity of the the formula that you need to deal with your SMT. Yeah. Okay. That you need that you will need to send to your SMT solver. Yeah. And that's what you're going to see. And I'll illustrate that using programming example, and you can see that since and you can extrapolate to neural networks as well. And later in the course, we will be getting to abstractions which are specifically tailored for for dealing with the complexity of verification of neural networks. Okay, so here is a program that I have shown in the form of a control flow graph. Okay, program has 3 locations, L0, L1, and L2. So L0 is the entry location. There is some initialization. So the label here on each of these transition here, going from 1, should be read as the statement, as the statement that is executed. Okay, at that location. So at location L0, there is initialization of the variable x. Okay, 2 to 2. Okay, the prime location here is denotes the value of the post variable. Okay, and I mean the value that it takes after the assignment. So the this is assigns to 2 L1 as long as x is less than 9, updating the variable x, x prime, to 2x minus 1, 2 times the original value, 2x minus 1. Okay, and you jump to location L2 when x is greater than or equal to 9. Okay. And there's no change when you jump to L2. And in L2, you iterate for x, as long as, you decrement the value of x as long as it is greater than or equal to 3. There is a typo here. Should be x greater than or equal to 3. As long as x is greater than or equal to 3, you keep decrementing x in a loop, in a self loop at L2. And when x becomes 2, you jump back to location L1. So is that clear? Okay, I hope that is simple enough. So there is this notion of, this also illustrates how you deal with loops in program. Okay, I showed you how to convert a formula into when it is straight line programs. When you have loops, it's a different ballgame. But I'm going to illustrate this in a very intuitive way, not in a very formal way. But I thought that the concept of over approximation is better handled with illustrated with a loop. I mean, that's when it gets interesting for in the case of programs. Okay, so an inductive invariant for a program at any location is defined as follows. It's a some predicate. Okay, predicate that characterizes a set of values that is true every time control is at that location. Okay, so for example, at L1, at location L1, what can you say about the possible values that x can take at location L1. So I showed you in that example, okay, how you could, make a predicate at each location to capture the possible values that the program variables can take at that location whenever the control reaches that program. So here, there are three ways to, and the way you kind of construct that predicate is to isolate the ways in which you can get to location L1. How many ways are there to get to location L1? You can get in three different ways. One, by this transition from L0 to L1, from the self-loop transition from L1 back to L1, or you can get from L2. So the set of possible values that it can take here at L1 has to include the initial value 2, correct? And let's see what these values. So in this case, as long as x is less than 9, you'll be doing 2x minus 1. So you will have, after first iteration, x will be 3. After second iteration, x will be 5. For the third iteration, x will become 9. Okay, so it includes all these values, after which you will get out. Okay, so the possible values that are generated by the self loop are 3, 5, and 9. So that is kind of added to that set of values. Okay, and in terms of predicate characterization, it is just OR. Okay, when you do an OR, it is like taking the union of the set of values represented by this conjunct, this disjunct as well as this one. Now, this transition from L2 to L1 doesn't add any new value, because when x is less than or equal to 2, you are just keeping that value. Okay, that's what it does. So, and that would be 2 anyway. So when you get from here, and therefore 2 is already included, because you get this only when x is less than or equal to 2. Okay, and x is equal to 2 is already included in here. So the predicate, the strongest predicate, by strongest I mean the one that captures exactly precisely the set of values that x can take when you're in location L1, is something like this. Okay, and the way that so that's that's what you will have to do in order to capture, in order to verify a program with loops in general. You have to derive these inductive invariants which capture the set of values, possible reachable values that at each location. How you do that is part of this whole logic theory. Okay, I'm not going to get into that. I want you to understand that it is indeed possible to capture these as some predicates that define precisely those values that the program variables can take. Now, can anyone answer if the initial value is, I'm sorry, I have to read it, I have some problem with mine, is between 1 and 2, what would be the predicate? Okay, I showed you. So in the interest of time, I will show you. So if x is equal to if the initial value, instead of being assigned to 2, if it is between 1 and 2, so I'm assuming here these variables are integer variables. Okay, so that's I should have mentioned that. So then it'll the possible values is also includes x is equal to 1. Okay, of course, if x is 1, then you never get out of this loop. Okay, so it's only for the cases where x is greater than 2. So the strongest invariant at L2 will be between 9 and 2, between 2, I'm sorry, it'll be 2, everything in the entire range from 2 to 9. Okay, that will not change. But so you get the idea. So that's how you have to be computed. So how exactly is this derived? I'll only a general way to characterize that predicate is something like this. Okay, for example, to L1, it is the predicate that precisely defines the exact set of values that the variable x can take at location L1. Is something as defined as follows. It can be defined in a recursive form. L1 is the smallest predicate that satisfies these two conditions. The initial, if x satisfies, is included in one of the initial values, then it has to be included as part of that predicate. That's what the first constraint says. Now, if x is a value that it can, so if it is already included and x is less than 9, then 2x minus 1 has to be in that set of values characterized by the predicate as well. Okay, that's how this thing is, so this predicate where I have enumerated all the possible values, which I was able to do because here it is only a finite set of values, can be characterized this way in a generic inductive fashion. I'm just giving you an idea to say that this is how, okay, if you want to do program verification, you will have to compute these so-called inductive invariants using whole logic, which actually specifies, gives you an algorithm as to how these things can be computed and how they can be automated. Okay, so as you can see, there is a lot of logical manipulation that needs to be done here, and all those steps can be implemented using SMT solvers as the backend engine. Okay, here in this course, our thing is not to do program verification, but rather to concentrate on this thing. But there is this theory, rich theory for program verification, which is what I wanted you to expose. Okay, it's already 6:15. So let me just take 5 more minutes. So some technical questions. Can you automate, as I've already said, to compute these kinds of predicates that satisfy these inductive thing? See, in general, it is undecidable if if the formulas that you need to model your program is within the full first order predicate calculus with all quantifiers and theories and rich theories. Okay, however, it is decidable for restricted logics, or as I said, by sacrificing precision. And that's where over-approximate invariance. Okay, there are 2 ways to do it. Either you restrict the expressive power of your logic, okay, severely, then you're able to come up with decidable, that becomes this problem of generating these kinds of inductive invariance will become, which is mostly based on this whole logic, becomes decidable. Another way, just kind of equivalent to that, is by instead of relaxing the goal of doing it precisely, if you're allowed to over approximate this invariance, okay, in the sense that in this sense, then it becomes easy. Okay, for example, by using what are called abstract domains. Okay, let's suppose that here our intention is not to capture the precise set of values in terms of predicate, but certain, and suppose I want to track only if the values are either positive, negative, or 0. Okay, So then you would have, this is one way of, kind of restricting what you want to track. Then you see the strongest thing that you can, predicate at L1 with the sign domain. You know that X is plus, okay, which is equivalent to saying X is greater than 0. So X greater than 0 not only includes all the values, but all the values that are all the possible values, but it also includes a lot more, correct? Because as you know that this is what I mean by if you're willing to lose precision. Okay, if here X greater than 0, it includes not only the actual values that this program may take at location L1, but not more than that. Now, if this is all that you want to do, so this is abstracting. You can see in this case a whole set of possible infinite values into one of these into a finite domain. Okay. So similarly, as you can see, if the initial value is between 0 and 2, then this simple thing, it can only be plus and minus, which is captured by X not equal to 0. So if you, and these invariance is what I call as over approximation, because they include not only the actual values that the programs can take, but they guarantee to include that and possibly more. In that case, I mean, you could prove, if all you want to prove is that at this location, is that X is greater than 0, then using such an abstraction will suffice. Okay, if you can fine tune, if the property is that you're interested is only whether certain variables are either plus, minus, or 0, then you can actually compute those invariants in an over approximate way. So an over approximation is something which includes all the possible values, the precise value that you take, but something more than that. Okay. Once again, the question is, can you automatically compute strongest inductive invariance over such abstract domains? Yes, these are over certain kinds of domains, like I've shown here, as well as certain other kinds of domains like interval domains, polyhedral domains, and so on. It is possible. It's not only decidable to compute, but there are efficient methods to compute them for restricted logics and restricted abstract domains. Another domain for which which works very nicely is interval domains. Okay, rather than having arbitrary sets of values, if you only track the values, whether those program variables take values within a certain range with a fixed max and min value, even then you can compute it. Okay, so for example, your strongest invariant, precise inductive invariant had exactly this, but in the interval domain, you could, this can be approximated to something by saying that it is between 2 and 9. You see, now this one is an over approximation of this, because this includes not only the precise values but other things. Now, but if you're interested only in, say, checking whether something's variables overflow or underflow, then an abstract domain with an interval domain is perfectly fine. Okay, is one can live with. Okay, and that is what an over approximation is, and therefore there are various ways. I've shown you some ways to over approximate the actual behavior. In this case, I'm modeling the behavior as invariance or the inductive invariance in the way that I have introduced. And this is by using these over approximations, your methods, the complexity of a verification task is made easier. Okay, I don't think I've covered all the points. I will continue with this a little bit more in the next class. Okay, so in the next class we'll be meeting on Wednesday. If I feel like I'm falling behind, I might take an extra class next week on Thursday. Okay, instead of the tutorial. I just want to give you a heads up for that. Okay, so I know that I've gone way beyond this thing. I apologize for that. So any questions?
No, sir.